Okay, thank you. Yeah, so what I hope to do this morning was give, well, for some people in the audience, is perhaps not, well, stuff they already know, but might be helpful for people to give a sort of an overview of what, as I understand it, are the main Monte Carlo methods, particularly used for solving neutron transport equation type problems in industry and in sort of the engineering context. And sort of what some of the algorithmic issues are, where I think there's still open challenges or where there's some interesting hard problems. Try and give some sense of, I think, how the theory matches with what people are doing. Our experience, we've been working with people for a while, is especially from the perspective of someone who's not necessarily an out-and-out engineering or programming person. Trying to understand what happens in a lot of the algorithms is not always straightforward. There's lots of different codes out there and so on that do slightly different things, and trying to understand that from a, I guess, a computational perspective isn't always straightforward, but hopefully I can explain a bit today in and hopefully in a language that, well, is suitable for the people coming from a more mathematical background rather than the engineering background, who will probably find everything I say very straightforward and perhaps not always 100% correct. So if some of those people like Andrea, Jeff, Eric, if you see things that I say that aren't quite right, please do correct me. I'll try and keep an eye on the chat. So I'm not going to go into lots and lots of mathematical detail. Mostly I'm going to be talking about several different sets of algorithms that come up. And the main sort of idea is really there's, as far as I can see, two sort of very well established applications areas that are substantially or quite different. I think we've had talks on both of these yesterday. So the first key application area is this sort of idea of criticality. Okay, so this drives a lot, particularly in the reactor modeling section. This is a lot of the sort of modeling that goes on in this session, but also connects into sort of some of the quasi-stationary stuff we had yesterday. So on a mathematical perspective, is really basically about finding eigenvalues. So the fundamental problem, we have some sort of nuclear system, so a branching system, we have particles coming out, we have particles being killed, and we think of this as being a nuclear reactor or something. And generally, we're going to run these systems close to criticality. We want to know really, if we're running a reactor in a particular state, what's going to happen to the reactor over time. What can we say about, so the sort of questions we might look at. So we want to sort of know what the system looks like in criticality. So this corresponds to basically a stationary state of the Markov process, if you want to think of it as a stochastic process. And we want to sort of know what this looks like. Well, one of the things we might want to do is to understand, okay, you're running a reactor, you have fuel rods in there, uranium or whatever it is that's sort of driving the reaction. But over time, of course, this uranium degrades. And as obviously the uranium degrades into whatever the off products and the byproducts of the nuclear reactions are, it's going to change the way the reactor behaves, where the particles are, what's going on. We may want to know, okay, what about secondary products? What sort of things are going to build up in the reactor? May want to know for operational reasons what typical reaction temperatures might be. We're designing a new reactor. We don't want it to get too hot. We want to be able to predict how much power it's going to produce, and that corresponds to how much heat it's producing. So what are typical temperatures? And also then what sort of byproducts appear. So if you're running a reactor, for example, there's phenomena like, this is called Xenon Poisoning. So that you get certain byproducts coming from the fission reactions. I think xenon is one of them, and this can build up in a reactor. And xenon, I think, is an inhibitor of reactions, so it will absorb neutrons, and because it's taking stuff out of the system, will sort of reduce slightly the criticality. And obviously, you need to be able to understand how these things are going to affect what's going on in a reactor over time. So understanding how xenon builds up over time might be part of solving, understanding what the reactor looks like in criticality and trying to extrapolate from that. So that's the sort of the first problem, which mathematically is really about finding a sort of an appropriate eigenvalue for a system. The second problem that comes up quite a lot is this idea of, it's called a shielding problem. So fundamentally, this is about I have some source of radioactivity. So now maybe this is some nuclear waste, or something that some sort of natural source of radioactivity. It could also be in the medical application, something like, okay, I'm using a proton beam or something. I'm going into a patient, and I want to know, will the people operating the machinery be safe if they're stood behind a glass door or behind a lead wall or whatever it is? How much sort of protection do I have to put to make them safe? So this, in some ways, is more general class of problems than criticality, which tends to really be about, well, obviously it's important in if you're building weapons, we hope you aren't. Obviously this is one of the issues, but I think the more common application for most people is in reactor design. The shielding problem comes up in a lot more applications. So I mentioned medical, also if you have space, so if you have astronauts in space or just equipment in space, it's subject to space radiation, and you may want to know, okay, what's the chance of, or how much radioactive dose will equipment or people inside a certain sort of type of shielding receive. So in the shielding problem, from a stochastic point of view, it's somewhat different. The idea is that we're often interested in sort of rare events, very rare events. So this is what Tony was talking about yesterday, and particularly what are typical paths for events reaching a detector. So I may have some sort of, you could imagine some sort of source of radioactivity sat here, which is emitting particles. And I might have a wall or something here, and a person stood here. And I want to know, okay, how easy is it for my radioactivity? I mean, it may get stopped by the wall, but maybe there's a little gap here, and I could have something that hits here, scatters, and does something like that. But of course, in order to do that, if I have a little gap, there's not much space for that to happen. So I have to sort of find a very specific path. Okay, and so some of these problems can involve quite complex routes, or you could also imagine in this sort of nuclear context, maybe if I have fissile material around, perhaps I have to go through a sequence of, that actually I have to sort of be a particular type of particle that is much more likely to make this long journey and not get sort of hit by something else. And so I have to sort of have a fission reaction to decompose into some other particle that's then going to shoot off in this direction, and then I have to have a lucky collision here. So typically if I just sample my paths randomly in some of these rare event problems, I may not actually get any or many particles coming to the detector. So estimating the sort of flux, the how many particles get from here to here might be quite hard just by standard sort of simulation techniques. So in these problems, the sort of challenges can be slightly different. Mathematically, they're different. And also things like, okay, in this shielding problem, we're typically worried about where the source is, how much stuff is coming off, how much radioactivity is it producing, what type of radioactivity. That's going to be a crucial question. In the criticality problem, we're looking for something to get into a stationary state, and actually typically with thinking about stuff which is at a state where there's lots and lots of existing activity, and any natural source of radioactivity coming from sort of natural decay of stuff in the reactor, for example, may be very, very minimal compared to the sort of what's being produced in the reactor. I think Eric mentioned some cases of very low or startup problems where in fact that's not quite the case, and I'll come back again a bit later to some of the cases where that might not be entirely true, but in most practical criticality problems we're interested in this. So move on. So thinking about the basics of what we're trying to do. So Emma sort of talked a bit about the underlying physics that translates into a stochastic process. We want to sort of try and compute. And the fundamental thing we're going to do is we have some physical model, which we're going to think of here as being our neutron branching process, which is just a collection of particles which do various things. So we've got the transport, which in our case generally means your particle just moves in a straight line. until something happens. So it could be that that something is it leaves the domain we're modeling, so it goes outside the edge of the reactor, and at that point you might just assume it leaves the system. So we can have a sort of a killing from exiting. If it keeps going in the same direction and gets stopped. We have scattering. So particles move in a straight line if they're going through some sort of physical object, or you might have water in your reactor. You might obviously have things like fuel rods. You'll have control rods. You may hit the neutron may hit some of the background matter, and in that case it might scatter in a new direction and change velocity, perhaps also change energy, direction, and so on. Particles can be absorbed by the environment, so you can hit something here and just, okay, you might change slightly the atomic makeup of what's at this point, but it will just get absorbed, and it might go to some sort of stable atomic isotope, which we just will stay there forever, and we won't see that neutron again. And then the other possibility is fission. So it may again collide with a fissile material, so uranium typically. And what will happen is it collides, and then when it collides, it splits the uranium into some other, well, into a bunch of different stuff. But the most important thing for us is that you will end up with new neutrons coming out, which obviously then, this is the whole point of the fission reaction, sustains the reaction, because now instead of one particle, you've got these three particles all going on. So in stability, okay, if you have a critical reactor, what you would expect is the fission generation, so these three particles here, is sort of going to be offset by loss either to the boundary or through absorption. Okay, so these three different processes will sort of balance out, and the net production of new neutrons will be zero, but you should end up with some sort of steady state of production, and production via fission and removal via typically leaving the system, or absorption will balance out, and so that the whole system is steady. So that, I mean, that's the sort of underlying Markov process. I've got a simple picture that I've created in a nice, so this is a nice example of a toy reactor, because everything can be done fairly easily, sort of in a hexagonal shape. So I can run a branching Markov chain on here. You start the particle, I think it starts somewhere like here. And I've just plotted the tracks of different particles and their offspring. And you can sort of see, okay, I start here, perhaps I'm heading in this direction. Okay, I hit. So in this picture, I think the red is fuel, so that's where branching is likely to happen. Green is sort of shielding. So these are the sort of the cases, and you might scatter a bit more. This black area here is a control rod, so it's something like boron, which will absorb lots of neutrons. And so the particles move around, they will scatter off stuff. And in some cases, you will see them, perhaps here, you can see quite a lot of activity as lots of new particles are created. So you might get branching events, which will send off particles in new directions, and they can get absorbed in various places as well. So what you sort of see here is just everything that's sort of been produced by just one original particle. And so that's sort of the basic dynamics. And particles will leave the system, they may get absorbed. I think you can see one getting absorbed here, for example. And the fundamental problem is going to be to work out how this is going. This is a nice model, because things like, so one of the fundamental problems we're going to see is direction becomes very important, because particles tend to travel in straight lines, right? That it really becomes important thinking about what is ahead of a particle, assuming it's going to travel in that line, right? Because, for example, I could have a trajectory like this, which might just miss fuel rods, versus a trajectory like this, which just catches the end of a fuel rod. So angular direction can really be complicated. Now, in this example, I can do everything in 6 directions, because it's got a nice structure. But of course, in many in real applications, that's just not going to be the case. So this is a nice example because I can have a finite state space, but in practice, of course, we don't have that. We also have energy levels or velocity, which can be, so effectively our problem is 6-dimensional. 3 spatial positions typically and 3 velocity directions, okay, or 2 angular directions, and a energy level is the other way of formulating it. So we sort of have a 6-dimensional space with this very non-homogeneous background structure. And because this system is very very sort of non-homogeneous, very spatially dependent, very heavily dependent on things like angular direction, deterministic methods can be problematic. I mean, they exist and they can do some things very well, but typically in most industrial applications, Monte Carlo is sort of seen as a gold standard. So partly because we have this very complex underlying geometry. So if you're trying to set up a deterministic solver, you need to understand what the geometry looks like. You probably need to, by geometry, I just mean the physical makeup, right? What this background looks like, right? So you might, and this is a toy example, but you need to understand what are the configurations of fuel rods, where have I got different elements. Also in practice, things like what are the atomic makeups of these rods, right? What percentage of what different element is it? Is it going to be? What's the chance of hitting all these things and so on? So the sort of the geometry by which I mean the background can be very complex. Many of the physical quantities we're going to look at are going to be highly sensitive to the energy. So I've got a slide in a second and I'll show you what that means. So, which means that, well, this slide here. So this is what's called the cross section. So this is from one of the nuclear data libraries. So energy here you can think of as the velocity of the incoming neutron. This is for some particular element. I think it's europium or something. The cross section here basically measures some sort of likelihood of a neutron being absorbed by this particular element as I sort of fire through the material at different velocities. And okay, this bit up here looks not too bad, but now you could imagine, right, trying to do some sort of deterministic model when your picture looks like this, right? The difference, if I do some sort of discretization of energy levels, inside any energy level, I could have quite a wide range, and this is logarithmic scale, so this is many, many factors, a very big range of difference in the likelihood of that particle being absorbed depending on the energy level. So in practice, you're going to end up with not some nice structure across energy levels of what's going on, but a really very, very complex relationship between things like energy or velocity of particles and how likely they are to be absorbed. So when we do simulation, or if you were trying to do that by some sort of deterministic method, you would typically look to discretize all your variables, and trying to discretize in a way that behaves well. Here is one element. If you imagine you might have 10, 20 different elements in a reactor that you might be worried about, and they all have profiles looking something like this, but with no particular common features, right? Where you worry about different energy levels, you might have to really, really worry very concretely about different sort of, if you are trying to do some cautious discretization, you'd have to look at a lot of these different cross sections. This is just scattering, this is just absorption, capture, not scattering. So you've got lots of different levels of complexity. Scatter angle is also, again, very complex depending on what's going on. So there's a real issue here, which just makes deterministic methods extremely difficult to work in full fidelity. Doesn't mean they're not good, but you can't get them to work in certain cases, but you get this very difficult problem of how accurate are my deterministic methods, given I probably can't deal with some of these sorts of issues. And then the other thing is this, okay, depending on where I am in the reactor, I may get very different types of behavior. So if I'm in, and you can perhaps sort of see it somewhere around here, if I'm in a fuel core, my particles may just be bouncing around and doing lots and lots of sort of very, very short movements. And so effectively, I've got a particle that's doing lots of stuff like this. And in the end, on a sort of stochastic level, it's probably not badly modeled by some sort of Brownian motion, diffusive behavior, provided it stays in the fuel rod. But as soon as I leave the fuel rod, and they will eventually, right, I'm probably going to be much less likely to interact. And so I will suddenly leave and have very straight behavior. So we might get something that looks like diffusive behavior and then a straight line, and then diffusive behavior and then another straight line, and something like that. So your particles can sort of move in quite non-homogeneous ways across the reactor. And again, okay, I mean, there are many codes that use diffusive approximations in the reactor at different levels, and sometimes they can work well, but you have to be have a good understanding of what's going on in order to make that approximation, and it could be very hard to quantify how wrong diffusive approximation may be. So, and because of these sort of reasons, basically most industrial level code now, combined, I guess, with increases in numerical power, means that Monte Carlo really is sort of a gold standard. It's seen as the way of getting accurate results for things like criticality and reactor design. And so everything I'm going to talk about today really is going to be pretty much Monte Carlo methods, and obviously this ties into, I think, the theme of what we've been talking about, which is how to use many of these Monte Carlo methods. So again, as sort of talking about background, there's a lot of numerical implementations around. The basic algorithms behind these different software tends to be the same, and that's what I'm going to try and explain. But there's lots of implementations around. I've listed some here. So Tripoli is the French one. So Eric and Andrea, I think, work mostly with Tripoli. Monk is the one provided by Answers. So Jeff and so on, people who are working on developing Monk. MCMP, I think, is from, I think it's Los Alamos, is a US open source version, or perhaps not quite open source, but relatively easy to access. SCON, I think, is one being developed in Cambridge. And effectively all of these, I mean, there's a lot of complicated things they need to do. One of the real difficulties is trying to work with the libraries of physical data that are made available, so cross sections and so on. How do you deal with them? How do you simulate your particles? How do you know where they are? How do you measure distances and so on? Also, how do you specify what your reactor or system looks like? And also then how do you, the other thing I'm not really going to go into is how you interact with other physical processes. So there's other physics going on in reactors, thermodynamics, you may have fluid dynamics if you have a water reactor or something that may also be important. So there may be things going on in the reactor that are not just neutron transport, which you may want to build in, because a lot of these things like cross sections may depend on temperature. So you may need to know what the temperature in the reactor at a given point is. So all of these things may have feedback effects, and all of these different software have different way of incorporating them, or different ways of dealing with them, and different implementations of the basic algorithms. Again, just to try and convince you that these things really are complex. I think Emma had these slides, but this is what a reactor model might look like. So I think this is some sort of pebble bed reactor, so lots and lots of small fuel pellets. Here's one with lots of rods of different fuel rods and so on in different arrangements and put together. And these are the sort of things you may want to try and model the particle transport in. So it's not a nice homogeneous system. There's no way you could solve this analytically. You really have to resort to mathematical methods. What's the main, okay, so mathematically, what's the main thing we're trying to do? So what we want to measure is neutron flux. So Emma introduced this. I'm going to quickly review the main equation. But for criticality, we basically have our flux, which you can think of as being similar to the probability density of neutrons. So from a stochastic perspective, you can think of this as some sort of probability density of where particles are. There's a slight difference, but it's not far off. And we want to look at reactors, or we want to solve a criticality problem. So if I had a stationary system or stable system, right, this is the flux at a given position. If the system is stable, then this is the effect of transport, so particles moving. This is the effect of, or moving in a straight line. This is the effect of particles scattering. And so these are the change in flux due to just movement and scatter. And this is my fission operator. So without this would be the number of particles being produced in the reactor. So I will lose particles here due to absorption and leaving the system. And I gain particles here according to the fission events. And basically, to find stability, it's a balance equation. If this isn't here, then I have a critical reactor if this equation holds. But in general, we may not have a critical reactor. What we want to work out is how do we make it critical? So the standard sort of industry way to do this is to sort of turn it into an eigenvalue problem. And we have a parameter K effective, which you can think of as being what the ratio of neutrons in one generation to the next would be if we didn't do anything to sort of kill them or get rid of them. So if K effective is 2, for example, each subsequent generation will have twice as many particles as the other one from fission. And the typical problem in a reactor might, the criticality problem is basically what number K effective do I need to put in here? So you can think of this as a killing factor. So if K effective is 2, I actually sort of kill half of my neutrons. So I would run my system, I'm producing twice as many neutrons as I need. So I can get stability if I basically just get rid of half of those neutrons. Okay, so I artificially say.
Excuse me, Alex.
Yeah.
Is it really killing half of the offspring, or dividing the fission rate by 2?
So so what we want to try and do in the algorithm, because the time at which fission happens is important, because the way we're going to structure it, a fission event, remember, is also a scattering event. So if my particle has a fission event here, these two particles will also change direction. So it looks like a scattering event. So mathematically, you could change the fission event, and this is sort of like the many-to-one stuff Emma was talking about yesterday. You can change the scatter rate, or so you can reinterpret the fission event as a scatter event and add in a weight on that particle corresponding to the number of offspring. And then this 1 over K effective effectively cancels those out. So you would change the number of offspring you produce on average. So you can interpret it that way, but you still have to have this scatter event. But you also, because of the way if I get to the algorithm in a second, it's also important to differentiate between fission events and killing events. So I would have to know that this was a scatter event that was a fission event, rather than a scatter event that was a scatter event, if that makes sense.
Mm-hmm.
So fundamentally, so there's lots of ways of interpreting this, and this is one of the challenges. So it could be that I flick a coin corresponding to K effective, and I produce 2, and then I just delete this one. But it could be, it doesn't mean I need to produce the 2, but it's important that this is a fission and not a scatter event for the sort of the accounting that's going to come on.
Okay. May I ask a second question? How is it physically implemented? So to change the fission rate or the number of offspring in a fission event.
So in a reactor, you mean?
Yes.
So okay, so here's my toy reactor. This here is I'm thinking of as a control rod, right? So it's typically, I think, boron or something. So something that absorbs a lot of the neutrons. So what you will do, I mean, you will have more than one of these, but what you will do in the reactor, I think, is you will try and measure something based on the temperature or the number of particles you've got going. If you think the flux is increasing beyond where you want it, you will lower your control rod. And now, because you have more stuff in the reactor stopping particles from moving, you're going to, so it's actually not changing this bit, but hidden in this scatter event is also an absorption event. So you've got the cases where this is absorption. And actually what you're doing is you're increasing the rate at which particles are absorbed.
Okay.
So you will try and do this in a way that tries to keep this at K-effective.
So it's actually another. Okay. So actually, it's you're solving another problem, but after some algebraic transformation, you get to this problem. Is that right?
So I think the difference is you don't. So when you design a reactor, I think the point is you will design, or when you do this calculation, you fix the reactor in some state. So you will do it, in such a way that K-effective will be pretty close to 1. But you say this is the current position of my control rod, and then you will want to know you will want to solve this system to find in that position what is K-effective, and maybe it's 1.07 or something. Mm-hmm. And then, I'm not going to talk about this today, and I'm not sure I'm 100% on the physics engineering here, but there's certain other measurements to do with lifetimes of particles and delayed neutrons and so on, which I might come back to at the end, where you can sort of measure, I think, timescales of reactors. But it involves things like this computation of K-effective. So you have some idea of how long it takes a reactor to respond, so what the timescale is of responses in the actual system are. Mm-hmm. But if I understand the way that the engineers and the people actually running these systems do, there's a calculation involving this K-effective and I think some ratio of delayed to prompt neutron emissions, which depending on what, some sort of calculation based on what's going on here, about what sort of timescales the reactor is running on in terms of how long it takes to respond to things.
Okay, thanks.
But to solve these, and maybe I'll talk about this at the end. I think that the numerics is just getting to the point where you can do real-time simulations. But I think the understanding in the engineering community, the physics community, has been based on trying to solve these types of problems and backing out from things like K-effective what some of these timescales must look like. Mm-hmm. Because you couldn't at least 70s, 80s, 50s, when people building these, solve these problems in real time. So you have to, but this is one you mostly can solve in real time. Mm-hmm. And if I understand, engineers and so on will have a much better understanding for what this K-effective actually means. And
they do call it K-effective, or is there another name?
I think K-effective, I think, is
okay.
Certainly not one we made up.
Okay, thanks.
So this is the equation we want to solve. So mathematically, Emma did most of the heavy lifting yesterday. The key thing we want is this neutron generational process. So a lot of what Emma talked about was in time. I'm going to talk about the generational process, which means I look at the positions of potentially weighted particles after n fission events. So if I start off with, which I think of as being a sum of Dirac measures mathematically, so just point measures where all of my particles are. Position is now position in space and velocity. And I think of this as where they are at the point where they just undergo a fission event. Okay, so I run my system to the nth fission event. And what we're going to look at mathematically is this semi-group here. which we can think of as being a nice way of interpreting this rather messy object, which is a measure. For those of you who are not so familiar with this sort of notation, this is a test function. So I'm going to write everything in terms of this test function, but this is a number, right, or a function of R and V. But the key thing is, actually, it's a number when I plug in a test function, and if I choose my test functions appropriately, right, by taking, for example, G as an indicator function of some set, 1 on some set of interest and 0 everywhere, I can do things like count how many particles are in some particular box. And effectively, I can then, by changing G, work out all the different configurations. So this G is just some nice mathematical way of encoding probability measures in a slightly more easy to handle form. And the nice thing, so the nice thing from a probabilistic point of view is this is now something that's open to Monte Carlo simulation, right? This is just physically start my particles, run them until the nth fission event, and then look at where they are. So this is something that's very open to Monte Carlo. And in fact, we have some nice results. So I can rewrite this in terms of various semigroups. And okay, I mean, this is sort of known certainly heuristically in the literature, but I think this is the sort of first time people carefully wrote this down. We know lots of nice eigen properties of these operators, these semigroups. In particular, we can find an eigenmeasure eta, this k effective as an eigenvalue, and an eigenfunction phi, where all of these nice properties happen, right? So we get a nice sort of spectral decomposition. And this statement here basically says, I start with a bunch of particles at position RV, I run them for n fission generations, and if I look at the configuration of my particles after n generations, I have this scaling factor k effective. I have some weighting factor that depends on my eta. So this is telling me that my particles are basically, remember this was my test function. So the position of my particles looks like this eta, and I get some weight function phi that will be important later that depends on where I start. So naive Monte Carlo just says, start with all these particles. I want to compute k effective. So I run my system. I look at the number of particles alive at time t. I take the log, divide by m. That washes away this stuff, and I'm just left with k effective. But I mean, so this is very naive. I mean, Min showed some results yesterday that sort of showed what happens. But effectively, if I don't have criticality, I've either got something that's growing exponentially. So if I want to run it for enough generations to sort of get rid of the effect of this thing and any stochastic effects, either my population size keeps growing, in which case numerically I have to keep track of exponentially growing numbers of particles, or it gets exponentially small, and of course stochastic effects are then going to mean that actually things die out. So actually, if I run it for large enough m, I'm going to have to run exponentially many simulations to get some that survive. Okay, and again, computationally, that's just not going to work. I want to sort of put a bit of a slide in to try and connect this theory. So theoretically, what's going on? We start with particles in some spatial measure eta naught. And when we do this operation, if we look at the spatial configuration, right? So there's this k effective n, but behind that we have some particle positions, right? So we're interested in two things. One is, what does the profile of particles look like, and what do they look like when we're growing? But if we just want to understand the spatial profile, the probability measure effectively, we can do that just by normalizing our population after each step. Okay, and so my particles at time m, I can compute by, well, where were they at time m minus 1? Let me run one extra generation, see where they are at this new position. So remember, this is my test function, so it's really what is the measure like? And I can renormalize by the actual population of what I see. And this is now on average. So I mean, this is now a normalized density. So effectively, all this is a sequence of probability measures. And there's a nice theory, and we get nice convergence. We get estimates of K effective coming out like this. But there's a nice theory, Pierre sort of hinted at this or talked about this in his talk yesterday. We get this sort of theory, you can call this a Boltzmann-Gibbs transformation, which is given now by the semi-group. And effectively what we're looking for is K effective is, well, the integral of eta against one generation, where eta is the fixed point of this particular Boltzmann-Gibbs transformation. There's another analytic way of expressing it, or we have nice properties going on. We have convergence, so eta is just the limiting application of this Boltzmann-Gibbs distribution. So another way of thinking about this generational process is we have a probability measure of particles. We run it for a generation. It comes back to this Feynman-Katz methodology. We run it for a generation. We have weights coming in depending on branching or killing. And so we get a new, no longer probability measure, but a weighted measure. But we can normalize to get back to a probability measure. And between the probability measures and the normalization factor, these two things tell us everything we want to know in the spectral representation. And effectively, I think this is so what people do in practice. So in practice, to try and solve these criticality problems, they run something called a power iteration algorithm. So I'm going to try and explain to you what it is with a slight simplification. Basically, we start with n particles, which is what's going to be our fixed level of particle population, and m generations. We start with a collection of n particles. We fix some initial estimate k naught of our K effective parameter. And now we simulate each particle in our current measure independently until it leaves the system or we have a fission event. When I have a fission event, and I should have some number new offspring on average, I will instead generate new divided by km offspring. Okay, so, and km is just my current or my estimate of K effective. I start with k naught, I choose whatever I think might be reasonable, maybe it's 1, and I'm going to update this estimate. And each time I'm going to renormalize my population to try and get close to n particles back. Because of course, every particle I end up with here is undergoing a fission event. I now have a new number of particles after fission, which will depend on what happened in that stage or batch. I'm going to normalize to n particles by copying or deleting randomly selected particles. So if I have a 1 to 1,000 particles and I end up with 1,100, I randomly select 1,000 of those 1,100 particles. If I have 990, I may copy 10 of them and add them back in. In practice, people do slightly more sophisticated things, but it's in this broad general area. And then I make an update to my K parameter. So I set Km plus 1 to be Km times the ratio of what I needed to what I had. And then I basically repeat until I'm done. So I go back to stage 2. I have new estimates, new particle positions, I keep going. And then I can estimate K effective based on some sequence of these things. Okay, so I throw away some initial bunch of particles and I update everything else based on, I use the rest to average to get some estimate of K on average. So that's a simplified version of the power iteration algorithm. I hope I haven't missed anything out. And you can do it. So if I do it in my toy reactor, this is generations on the bottom. Sorry, the scale is not very clear. This is 50 here. So I've done it for 250 generations. This is each time what K effective is. In my toy reactor, I can compute the true value, which is this red line. And what you can see is actually it converges pretty quickly to give me good estimates of K effective. So I'm just running this power iteration, looking at how many particles I expect to produce, and I get some sort of estimate and some sort of variance. And then what I would do in practice, well, in this case, it's a pretty small reactor, so this convergence is very quick. I might choose to average, say, 90% of these things to get something, and hopefully you can convince yourself that that's probably going to give us something pretty close to this K effective value. So that's the standard approach. for this. As I said, I mean, I don't think it's seen like this, particularly in the nuclear literature, although I think they understand that there is interaction going on here. From a mathematical perspective, I think it's very much in the framework of interacting particle systems, the sort of stuff that Pierre was talking about. You can also make strong connections to what Andy was talking about yesterday in terms of computing quasi-stationary distributions of these particle profiles. In most examples, this convergence for k-effective is fast. So just running this simple algorithm gets us k-effective pretty quickly. I mean, there are a bunch of papers around. I think from a mathematical perspective, I mean, these papers try and do sort of variance analysis and so on of these estimates. There are, from a mathematical perspective, I think quite a lot of assumptions and sort of hand-wavy arguments in these, but I think there's lots of experimental validation that people have some understanding of what's going on. But one of the things that's particularly, I think, difficult to understand is what correlation properties might look like. So how do we understand correlation in here? And in particular, actually, well, I'll come back to this in a second. As I said, rather than throwing away particles or duplicating, often some sort of particle bank is used. Often the difficulties come not so much in computing k-effective, but we also want to try and understand what the stationary flux looks like. And we can do this using what are called tallies. So this is some way of counting up the number of collisions happening in a given sort of bit of space direction energy. And if you want to compute things like burn-up rates, that's what you want to look at. But one of the difficulties now comes, okay, I want to understand perhaps how many particles I'm seeing, what the burn-up might look like in a sort of a cold bit of the reactor, somewhere that's perhaps not in the middle of a fuel rod. But this might be hard using Monte Carlo because all my particles are going to be mostly hanging around in the areas where fission is happening. So one of the challenges comes how to understand not so much this k-effective estimate, but the corresponding tallies, so counts of what's going on in other bits of the reactor, which I might want to understand, so to understand how the reactor is changing or behaving over time. And to do this, one of the things that people do is variance reduction. And I mean, I think this is less used on the criticality side. We'll come back to the shielding element in a minute, but there is some work. So mathematically, what we want to try and do is use an importance function. So Min talks about this, or an H transform, Duve H transform, to bias paths towards areas of interest, but use a weight to ensure the expectation remains unbiased. There is some work on this in the Monte Carlo literature, the nuclear Monte Carlo. I mean, these things tend to be called zero variance schemes because if you choose this H correctly, you get no variance. And of course, this corresponds to this adjoint function phi, which I had somewhere up here, this thing here. So it turns out the correct choice of H is the phi that comes out of this equation. And I think there's various ways of trying to solve this. So there are various ways of trying to use deterministic solvers to try and approximate phi. And the other thing that I think is fairly recent in the literature is this idea of an iterated fission probability. If I understand correctly, it's effectively using this representation here. So I start particles at different locations. I use effectively want to compute this phi n, but normalized by this quantity here. So I start a bunch of particles from different locations. I simulate my criticality. I use this iterated fission, the power iteration method to try and come up with estimates of k-effective for different starting points. And I compare these to get an estimate of this function phi. But of course, again, this is, I mean, in a big reactor, there's a limit to how much you can do this, and I can't do this at every point. So I have to try and, again, do some sort of discretization of space to work out where I'm going to compute these. But I think this is probably the sort of, or this and its variants now, is sort of the state of the art in this for criticality. Sorry, so this is basically what's going on, right? You compute it for different values and estimate by Monte Carlo. So it's a Monte Carlo way of trying to compute this function phi. So sort of, let me try and move on. What else do people do? There are lots and lots of other versions of variance reduction that go into this software. Lots of different pictures. Typically, our particles end up picking up weights because of either this variance reduction, the biasing, but we also get things like population control. So we have to try and keep a fixed number of particles. So in the nuclear literature is called population control. Normalization of measures. Again, this is really where the interaction between particles comes in. Other things they use are things like Russian roulette. So we have weighted particles, weights typically coming from things like this. Well, the biasing, we can use Russian roulette to try and, if weights of particles get too small, basically we want to try and, there's no point simulating a very small weight. So you kill it with a given probability, and you can make this a fair game by increasing the weight if it survives. You can do the same thing if the weight gets too high and split into multiple particles. You've got implicit capture, where you, rather than absorbing particles, you reduce their weight approximately. And I think in the algorithms, often rather than doing all these things immediately, you have these weight windows where you can sort of actually say, okay, I'm only going to do this Russian roulette if my weight goes below some spatially determined perhaps level. And there's, I think, software that determines what these weight windows should be based on these adjoint functions and so on. I mean, all of these things I think are theoretically justified in various ways. And there's sort of a less, well, I think theoretically understood trade-off here, which is about how to control these things, what the best way numerically is to try and fix these things. Lots and lots of practical experience in the industry about how to fix these things, lots and lots of different rules of thumb, applications. But effectively, all of this stuff is about how do I manage the evolution of my measure of particles, so my interacting particle system, in a way that follows as much as possible the process I want to do, while keeping particles in areas of interest. Okay, so I think there's a big question here about how to try and do this well. There's lots and lots of ad hoc methods, but perhaps not much theoretical understanding of how to do these things well. So yeah, so lots of big picture sort of talking here. Lots of ways of thinking about stochastic representations of this semigroup phi n. From a theoretical perspective, we've seen this H transform methodology. We've talked about many to one in Emma's talk. So using weights instead of branching. There's a practical perspective, lots and lots of ways of, in practice, people try and do this. I think Pierre's point yesterday, effectively all of this is just doing the same thing. There's some underlying flow of measures. These are all just different ways of balancing out this one measure. There's a question though of actually how do we tune some of these different algorithms? Partly also, I think when you want to worry about, okay, here's my, I can think about here's my evolution of measures. But if I'm going to look at my measure valued evolution, and I'm really interested in getting a good estimate of particles here, how might I build that into the evolution of my sequence of particles? How can I handle my particles in a way that might better reduce variance of estimates of sort of locations of these different particle values? Again, I mean, and then this connects into a lot of other existing literature, so interacting particle systems, sequential Monte Carlo, got some people talking about that today. Can we try and use all of this to understand these algorithms better? Things like also how do we handle parallelization. Everything here is being done on parallel computers. Interaction becomes an important part of that parallelization. How do we manage that? Are there clever ways of doing biasing, of working on individual particles? So in the branching literature, there's a paper by Threya. I think there's a more recent paper by Nick Whiteley, Anthony Lee, where they look at this in the context of SMC. So biasing individual particles, so choosing special particles and changing the dynamics of individual particles to try and get better convergence rates of things like variance. Can we do that without doing full variance reduction on all particles? Also, what can we say about things like genealogical structure? Can we use this to better provide, we had a clustering discussion yesterday, can we try and say some things more about clustering in there? There's other things that go on. I'm running out of time, so I'll skip over this, but the slide should be online. There's things like, there's lots of other tricks people use. So there's something called violent acceleration, where you actually have in extra generations, which gives faster convergence of these things to K-effective. Superhistory powering, we have more branching events in each generation. So I think this is common in, I think Monk is one of the big examples of this. Lots of challenges. So I've talked about clustering. Another big question, I think, that has partial answers in the engineering literature, but I don't know how, whether theoretically they're all that satisfactory, is how do we know when we've converged? So I think the current method is based on Shannon entropy. So we look at effectively the Shannon entropy of the particle picture at any given state. I think there's a slide here. So I mean, this is an example of a reactor. This is the computation. So this is from a paper by Forrest Brown. This is an estimate of K-effective. You can see it stabilizes incredibly quickly in this type of reactor here. But actually, if you look at the Shannon entropy, it suggests that it's not stable until about 1,500 generations. So the K-effective looks like it's stabilized, but the Shannon entropy hasn't. So if we're using, I mean, if we just looked at K-effective, we might say, well, I can compute tallies based on basically all of my particles, all of my batches. If you look at the Shannon entropy, that suggests actually you should be throwing away a lot more batches to get good estimates of things like, okay, you can see what might be going on here, right? Maybe I've got too many particles here and not enough here, but roughly the growth rate here and the growth rate here will be the same. So I need longer periods for my particles to move across. So that's one challenge. The other thing is just how do we fix a lot of these parameters in different problems? Sort of rules of thumb, but no, I think there's a sort of lack of theory, so I'm trying to justify or explain some of this. Okay, the second set of problems that I want to talk about are shielding. I said at the start, okay, what are we interested in here? I mean, often these are called fixed source because we're really worrying about where particles are coming from. Generally relevant, we're thinking now about subcritical cases, so all our particles are dying out, being absorbed, leaving the system at some point. We just want to know, on my trajectory when I leave the system here, did I go through some detector on the way? Okay, and these are things like, okay, if I have nuclear waste, am I shielding it correctly? What happens if I drop my container and it has a crack? Will it still be safe? Space radiation health applications, fusion reactors, they're generating lots of particles. If I want to run a fusion reactor, how do I do that in a way that is safe in terms of what's coming out of it? Mathematically, I think it's moderately simple. We go back to this sort of equation here, but instead of a fission term, you can have fission, but I'm going to ignore it. You have a source term, and this is the equation that dominates the particles. What you might want to know is what is the response at some detector D from the flux where I integrate against some function G, which is supported on some detector D. So I may have a source over here, a detector D, and I want to know how many particles end up coming through that detector. And I think there's two variants of this problem, two sort of difficult bits. One is mathematically difficult, I should say. One is sometimes these can be very, very rare events. Okay, I mean, I may, if I just did it naively, I may just have to do far too many simulations to get anything reaching my detector. So if I want to estimate probabilities, I just cannot do it numerically. The other challenge is perhaps not that things are rare, but I may want to know what my flux looks like on the route to the detector. So if I look at all the particles here that are reaching here, okay, how did they get here? So perhaps I want to know, okay, maybe I have some region here where something is not so certain. I don't quite know what's in that. I want to know, okay, suppose I make some change to my system here. How many of the particles reaching the detector went through that location? Okay, so now not only do I want to know the probability of some rare event, but also the probability of some rare event given something that happened over here. And so then, I mean, mathematically, that's okay, not so hard to generate the paths, but harder to generate the paths that I'm interested in, and therefore minimize variance and so on. So again, and I think here it's much, much more classical to use this. There's lots of ways of doing, I think in the nuclear literature it would be called biasing, in the mathematical literature it would be called H-transforming to compute new laws of the process. Mathematically, you can do this. Sorry, there's a slide that I will skip over. I mean, but I think this is all basically standard. The key point is you end up having to introduce, when you do a weighting with an arbitrary function h, you have to introduce some weight biasing here. Okay, so I want to look at particles that hit my detector, but which I attach some exponential weight to based on my operators and my h function. This weight, there it is going to be 0 if I can choose a function h which satisfies this. But this choice of h is exactly the adjoint flux. Okay, I mean, in the case where, which we saw before, but with 0 fission. Okay, and then we're going to compute dynamics under this changed transform, but I'm going to hope I can get an h. Well, I can't solve it exactly, but maybe I can get an h which is close to 0, and then this variance, if this exponential term is small or always close to 1, this variance then should be relatively well controlled. And this can be done. So in fact, what exists quite a lot in the literature, so this is a slide from one of Eric's papers, is lots of, I mean, there is quite a lot of different methodology now for computing these weight functions or importance maps, H functions. So this is an example using a variant of this CADIS methodology from a recent paper by Eric. This is what's in the Tripoli software. So you can imagine the problem here. I have a source, I have a wall, and I have some little inlet where maybe the wall is easier to get through. And the question is, how does that affect particles reaching a person stood here? So this is just my importance map, which I might then use to feed into a simulation, but in general, these importance maps really help simulating these events. This CADIS is a deterministic methodology. There's I think, a second methodology based on Monte Carlo methods, using what are called response matrix approaches. So this is from a paper by Leppänen. And here again, he's trying to do the same thing. So computing this adjoint flux, I think this is some fuel container. And this is an iterative process. And this is what you get after, I think it's about 50,000 Monte Carlo trajectories, your estimates of the adjoint flux in this system. And you can see the importance map, I think in this case is being created by or denoted by this scale here. The other method that I'm not going to go into, I think has a lot more connections to this interacting particle systems, is this adaptive multi-level splitting, which Eric and Tony both worked on. I think is much more promising in some ways for trying to do some of these, especially for the really rare event stuff. Again, I would strongly, well, talk about Tony's talk. I think there's also, again, strong connections to the interacting particle systems that Pierre talked about, that Andy talked about. Again, you can think of it in a similar vein, I think, as this sort of rare event simulation. I would say, I mean, I think there was a question in one of the talks yesterday. So this is from a paper by Eric and co-authors. I think they actually used this importance map in the AMS methodology. So I think someone asked whether it had been done yesterday. I think the answer is Eric has done it in this paper using this sort of importance map. I think the results were very promising. I hope that's right, Eric. And then, sorry, maybe 2 more minutes just to talk about the sort of future challenges that I think are very interesting and offer difficulties on top of this. So something called dynamic Monte Carlo. There's a question in the start about these criticality calculations. It may be that we want to understand what's going on in a reactor in real time. So as we were talking about earlier, you may want to raise or lower a control rod. So we want to try and understand what happens to the flux in a reactor. So that's this picture here. And I think this is, you raise a control rod at this time, and then you lower it again at this time. So what happens to the flux? And effectively, to try and understand what's going on, you need to solve this thing using Monte Carlo in real time. Or if you're doing it via Monte Carlo, you have to solve it on a real time scale, because there's a real problem here, because typical generations of particles are of order of 10 to the minus 5 seconds. So that's time between fission events. But we often create precursors during fission events, and these precursors decay over much longer timescales, so of order perhaps 10 seconds. So what's going on in the reactor here can really be having an impact on timescales up here. So if we see a sudden jump here, the time it takes for that to filter through can be of order tens of seconds. But in order to be doing Monte Carlo, we need to be doing it on order 10 to the minus 5 seconds. So there's basically a timescale issue here. And to do that, well, this is the first problem, because you have to run your Monte Carlo batches over very small timescales, and you have to run lots of them to make sure you get to the end. So there's lots and lots of scope here for variance reduction, all sorts of things going on to try and ensure your Monte Carlo on these time steps, well, effectively to try and allow yourself to run for longer time steps. The other issue that comes up is I think this is from a paper of Andrea's, a recent paper. And if I understand right, the number of precursor neutrons you would have in the system at any one time is of order 10 to the 4 greater than, so these are ones that are currently waiting to decay into a neutron, but are in some isotope somewhere, is of order 10 to the 4 times the number of particles that you might have actually active. So if you're trying to do Monte Carlo and just storing all your precursors and saying, oh, well, they're in some state waiting to become active, you have many, many more particles that you have to store than the ones you're going to simulate. So you just cannot store all of them and wait for them to decay. So you have to come up with clever ways of handling that. I think that's, I've gone over a bit, but that's what I want to get to. I mean, what I wanted to try and just summarize, I mean, tell you what's going on. What I see as interesting from a mathematical perspective about what's going on in the Monte Carlo side of neutron transport. With a mathematician's eye on, I think there's pervasive use of sort of variants of interacting particle models being used in practical ways, along with lots and lots of other tricks. So there's lots of, I mean, I think experimentally all of these are very well understood and justified, but I think mathematically there's lots of question marks over how they work, what are key to them working. Can we, I mean, there's lots of sort of rules of thumb around about how many generations you should run for this, or what sort of parameters you should put in, but there's lots of parameters floating around that often don't have a lot of theoretical justification or understanding. I mean, interacting particles literature has undergone lots and lots of developments over the last 10, 20 years. It's not clear to me that a lot of this has fed through to the nuclear transport literature. And I guess there's a question of where it might feed through as well. What can we say that's helpful from interacting particles that we can bring through to some of these simulation techniques, or even vice versa, other interesting things in the nuclear industry that people have been doing that might be relevant in the interacting particles literature. But, okay, I'll finish there. And there's 2 references of stuff I think I've found helpful in terms of where a lot of this this theory is. It's not always so easy to find, but there's a couple of handy references for people who want to find out a bit more about it. But, okay, I'll finish there.
Thank you very much for a wide-ranging talk. So I'm sure people have all sorts of questions, but since we're already behind time, may I suggest we take a break first, and then there's a discussion session just afterward, and then there'll be more time for, I think, questions and discussions. Would that be all right? Yeah.